So now that we're done with derivatives, we're moving on to what's called integrals, and it starts with area and estimating with sum, like adding. So your objectives are to be able to solve problems involving area, distance, average value, and examples of estimations. So while you're studying this, is a great achievement of classical geometry was obtaining the formulas for the areas and volumes of traditional shapes like triangles, spheres, and cones. In this chapter, we develop a method called integration to calculate the areas and volumes of more general shapes. So ones that don't have sharp lines or edges. The definite integral is the key tool in calculus for defining and calculating areas and volume. So what you'll see is, well, let me just do a general thing. If we have y is x cubed, we've said y prime would be 3x squared and y double prime would be 6x. On the other hand, if you're going backwards, you'd say go up a power and you need 1/3 or 1 over that power. So in other words, if you go on y prime is x squared, then y would be 1/3 x cubed. Now, that part we wrote before. Now, the notation for it would be like this, the integral of x squared dx. But now, what you're going to get to in a little bit are definite integrals, and those would be like things like an integral from 0 to 2 of x squared dx. And so on those, you're going to have a definite starting and stopping point. Oh, sure. Yeah, that's fine. No problem. Oh, I didn't realize I was still recording. Oh well, just got a interruption. Okay, so where were we? It's called the fundamental theorem of calculus when you're doing your antiderivatives and integrals. So we begin our approach by approximating these with simpler, finite, or limited sums related to these ideas. We use the term upper sum and lower sum related to adding areas under a curve. The true value lies somewhere between them. So for example, say you have something like that. Well, you might have lower rectangles like that. And you might have upper like that. And I know sometimes on some problems there is a midpoint. So lower, of course, means below the curve. So that estimate would be too small. On the upper, the estimate would be too big. And so we're going to discover different approaches. Midpoint's probably one of the best approaches. Another estimate can be obtained by using rectangles whose heights are the midpoints. That's what I was saying, the midpoint It's called the midpoint rule for approximating area. The midpoint rule gives an estimate that's between a lower and an upper, but it's not so quite clear if it overestimated or underestimated. By taking more and more with them thinner, it appears it's a better approximation. So sometimes we don't know whether the midpoint will be too high or too low, but at least it will be closer. So the midpoint will be closer to the actual area, but we don't know if it's too high or low. Remember that the position function has derivative velocity. If we can find the antiderivative of the velocity, then we get the position, and we have to do this extra plus c part, which is some constant. The constant could be 0 or it could be a random number. It depends on the problem. The distance traveled can then be found by calculating the change in position. So this might be similar to what we've done before in physics. We will approximate the distance traveled on each subinterval using the distance formula. Distance equal velocity times time. Just think meters equal meters per second times seconds. So the S's cancel. Also, we're going to talk about displacement versus distance traveled. Displacement is the difference between the initial and final positions. It's not the total. To see a difference, think about what happens when you walk a mile from your home and then walk back. The total distance is 2, but your displacement is 0 because you end up where you started. Average value along a non-negative continuous function. So non-negative is 0 and positive. The average value is found by adding them together and dividing by n. Think about a snapshot of the height of some water that's sloshing around in a tank between the walls at x equal a and b. As the water moves, the height of each point changes, but the average height remains the same. To get the average height, we settle it down till it's level, and you have a constant height. And the resulting height is the area under the graph. Okay, so let's look at page 255. So what they're showing is that you have water that could be, above or below, but then once it settles down, then you'll have a constant height. And here's again what we mean on the rectangles. This one is using a sine curve, and we have the midpoint basically, because some are above, actually, yeah, all these are above and all these are below. Okay, so the summary is the area under the graph of a positive function, the distance traveled does not change direction, and the average of it over an interval can all be approximated by your finite sums. The true value lies somewhere between the approximations by the upper and lower. In the examples, the finite would be better if you get thinner width and more. Okay, so here we go. So one thing I do want to mention before we even get started is this is a problem where it wants a decimal, not a fraction. You know, most of the time the default for Math Excel is a fraction. But when I did this problem before, you have a lower two part and I got a 1/8 and so forth. Now these were probably just because it's x squared between 0 and 1 that I have such small numbers. So there's a lower 2 rectangle, a lower 4 rectangle, an upper 2 rectangle, and an upper 4 rectangle. Now my note to the side was Math Excel wants decimals. So that's what you're going to do over here. Now, this is kind of going to be faint, but this was an example with 8x squared going from 0 to 8. We did our delta triangle and say 8 minus 0 over 2 to get 4, and then say xi is 4i. And then for two rectangles, we go 0 to 1, and you think 8x squared, so it's going to be 8 times 4i squared. And then figure out what that is, and then simplify it and get your number. So that's for the first part, and then you go from there with more. Okay, so let's do that with ours. So our first step is, notice we have 3x squared, and we're going from 0 to 14. So on this one, we first say delta x is going to be 14 minus 0 divided by 2, which is 7. So that means xi equal 7i. Now, for the two rectangles, we need to do the sum, which is that fancy E. It means add up from here to there. So add up from the lower end being 0 to 1. That means start at 0 and then you have 1. So that means two rectangles. Now compare that to when you do the upper. On the upper, you're going to start at 1. Well, I'm just going to say I equal 1 and go to 2. So that is going to be the difference, why there's different ones. And also, like, what we'll go ahead and say before doing anything else is this is lower with 4. So this one you're going to do the sum from I equals 0 to 3. And this one you're going to do the sum from I equal 1 to 4. So that's how they're going to be different. So that's why you need to figure out the first and then go from there. Now, for the lower, for two rectangles, we are using 3x squared. So that means 3 times what we put here, which was 7i squared. And then we need to multiply by 7. So the reason to multiply by 7 is because when we're doing this, we use dx, or you could say triangle x, and that's going to be 7. Okay, so that's how we do that. And so we're going to do 7 times 3 is 21 times 49i squared. Now that's going to give us a big number. 21 times 49 is 1029 I squared. And it looks like, at least on this one, we just drop off the I squared. So what we do with this is we then have to use our sum. And so when I equals 0, then you just have 1029 times 0 squared. So that's 0. And then when I equal 1, you get 1029. And so that is our answer, because if you add 0 to this, we do get what we want. Now, this is not like an I squared being an imaginary number. It's literally like a counting variable. So I is a counting variable. Kind of like used in sequences. Okay, so let's do lower with 4 now. So the good news is we already know what 0 and 1 is. So when I equal 2, you'd say 1029 times 2 squared. And that's 4116. And when I equal 3, I think I'm doing this a little bit too fast because we're supposed to divide by a different number. Let me just slow down a bit. So we do the sum from 0 to 3, and we have our 14 minus 0, but this needs to be divided by 4 instead. So our delta x equal 14 minus 0 divided by 4, which is 7 halves, or you could say 3.5. So that's going to change our numbers a bit. Okay, so let's think about it a little bit. We've got 3.5 for delta x, which means xi will be 3.5. I'm just going to put it right here. Xi equal 3.5. And so now we need to do your thing like this, where it's going to be 3 from the equation, and then instead of 7i, it's going to be 3.5 I squared. Oops. And then times 3.5. Okay, so let's get that. 3 times 3.5, and then you multiply by 3.5 squared. So that gives us 128.625. 128.625, and I squared at the back. Okay, so now we have to do these and say 128.625 times 0 squared plus 1 squared plus 2 squared plus 3 squared. And that's where we stop, right? Because we went from 0 to 3. 0, 1, 2, 3. Okay. So this would end up being 128.625 times 9 plus 4. Actually, let's simplify it. 10 plus 4 is 14. Okay, so that times 14 gives us 1800.75. And that was what we were expecting right there. So on the first go round, I didn't have your parentheses because it was only 2 terms and we only used the second. But now with having 3, it's easier to just do it like this. Okay, so now we're going to do upper, which we said we're going to go from 1 to 2. And if we're back to having 2 rectangles, then we use 7 again. So this was 3 times 7i squared times 7. Now that's actually going to be the same as what we had before, 1029i squared for the upper, because it's the same, basically same formula, but then we have to plug in different values. So this first one was the lower, this was the lower with 2. And this was the lower with 4. Now, when we do the upper with 2, we're going to say 1029 times. Now, here's where we're going to skip 0, and you're going to start with 1. So 1 squared plus 2 squared. So that's really 1029 times 5. 1029 times 5 is 5145. Then we need to do our upper with 4. So we're going to do 1029 times 1 squared plus 2 squared plus 3 squared plus 4 squared. So this one will be 9 and 1 is 10, 10 and 4 is 14, 14 and 16 is 30. Okay, let me just double check. 1 squared plus 2 squared plus 3 squared plus 4 squared. That gives us 30. Oh, I did it again. Okay. I should have used this 128 part. I knew better than that. It's just been a while. So 128.625 times 30. And that gives you your 3858.75, which is what we wanted. Okay, so there's the first one. Now we want another one very similar to that, but this time we're using 5x cubed. And so first thing we'll do is we'll say delta x is, okay, if we're going from 0 to 2, we have to do 2 minus 0 over 2, which is 1. And so xi equal 1i. And then we're going to do our sum from I equals 0 to 1 of 5 times 1i, or just I cubed. So that gives us 5i cubed. And I didn't put in the extra 1, but that's okay. So we have 5i cubed, and then we basically say 5 times 0 cubed plus 1 cubed, and so that just gives us 5. So the first one always seems to be the easiest. The next one, we need to do the sum from I equals 0 to 3, and we need 5 times something. Okay, so let's be careful about this one. We're doing 4 now, And so our delta x is going to be 2 minus 0 over 4, so that's a half. Or you could say 0.5. And then that means that xi would be 0.5i. So this is where I need 0.5i cubed. And then we need an extra 0.5 here. So then we want to multiply 5 times 0.5 and multiply by 0.5 to the third. And so that gives me 0.3125 I cubed. Now, with that, we need 0.3125 times 0 cubed plus 1 cubed plus 2 cubed plus 3 cubed. So that's 0 plus 1 plus 8 plus 27. And that gives us 11.25. Okay. So now for this one, for the upper with 2, we take our 5 and we go 1 cubed plus 2 cubed. 5 times 1 plus 8. That gives me 45. And then on this one, you take your 0.3125, multiply by 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. And so that'd be 1 plus 8 plus 27 plus 64. And that's 100. And so 100 times 0.3125 gives you 31.25, which is what we wanted. All right, so all those matched. That is a good stopping point for this video. Hope that helps.